Okay, now we are going into the topic number 5. So we have gone through topic 1, 2, 3, and 4 for the past, I believe, 8 weeks, right? So for today, we are going to focus on two-dimensional compressible flow subsonic over the airfoil. All right. So let us see what are the content in terms of this particular topic number 5. We will have 8 subtopic altogether, right? Starting with overview. The next one is the velocity potential equation, and then 5.3 is the linearized velocity potential equation. So basically, we will try to cover for the next hour on the subtopic of 5.1, 5.2, and 5.3. All right. And of course, we are going to have a short break between 5.2 and 5.3. And then we will continue the rest of the subtopic 5.4, Prandtl-Glauert compressible correction, improved compressibility corrections, critical Mach number, and the area rule, and finally the summary in our session next week. So for today, we are going to just focus on the first 3. Bear in mind that it is quite theoretical, right? The topic that we are going to go through today is quite theoretical. The example will be given next week for 5.4 and so on. Before we go any further, it's best to look into the overview. What is actually this particular chapter or particular topic all about? Basically, the present chapter number 5, deals with airfoils in high-speed subsonic flow. And what happens actually when an airfoil is flown at high subsonic Mach numbers, especially near the speed of sound, and how does compressibility change the airfoil properties and by how much? Okay. At the same time, we want to know how do we analyze and calculate these compressibility effects, right? Among other, those questions will be answered in our session today. So in addition, we will also see that as Mach number 1 is approached, going into the sonic region, right? The drag of an airfoil suddenly skyrockets. So the increase of drag. So you can see that the drag coefficient is increases and looks like it is going out of sight. Then so-called sound barrier, as sometimes referenced in the popular literature. What is actually going on here, and how do we deal with this situation? All right. So basically, what caused the early concern about sound barrier? When we see there's an increase in the drag. So in this present chapter, in this chapter number 5, it is also, if you refer to the Anderson book, it is a chapter number 11. All right. So we will develop a theory which is applicable to high-speed subsonic flight, and we will see how the theory predicts a monotonically increasing drag going to infinity as m Mach number infinity approaches 1. Specifically, so the purpose of this chapter is to examine the properties of two-dimensional airfoils at Mach numbers above 0.3. As we know that above 0.3, below 0.3, it is considered incompressible. So above that, it is compressible. Where we know we cannot assume incompressible flow because it is already above 0.3 Mach number. But in this case, we are going to focus what happened below Mach 1, between 0.3 to Mach 1. So in the process, you will observe that we only treat one-dimensional cases such as normal shock waves and flows in ducts. In later chapter, we will look into flow in ducts. Even oblique shock waves, which are two and normally three-dimensional in nature, depend only on the component of the Mach number, normal to the wave. Therefore, we have not been explicitly concerned with multi-dimensional flow. All right. So consequently, note that the types of equations which allow an analysis of these flows are algebraic equations. All right. So from time to time, we will see many relevant equations that are going to be used to solve these particular problems, and hence are relatively easy to solve in comparison with partial differential equations. So these algebraic equation that you are going to go through today were obtained by applying the integral forms of the conservation equations to appropriate control volumes, where the flow properties were uniform over the inflow and outflow phases of the control volume. So imagine we have normally we have a designated control volume. So we have properties inflow as well as properties outflow from the control volume. So we will apply the conservation equations to the situation. All right. So however, for general two or three dimensional flows, we are usually not afforded such a luxury. Instead, we must deal directly with the governing equations in their partial differential equation form. So indeed, for the remainder of our aerodynamic discussions in the topics that we are going to cover today as well as the following weeks, we will appeal mainly to the differential forms of what we call the continuity equations, momentum equation, as well as the energy equation. So we will refer back to the equations that we used earlier, right? So the roadmap, as usual, for this particular chapter is given in this figure, roadmap for chapter 5. So we are going to return to the concept of a velocity potential, right? So we start with a velocity potential equation, and then we are going to combine our governing equations to obtain a single equation simply in terms of velocity potential. So that is, we are going to obtain for compressible flow. So because it is Mach number more than 0.3, okay, an equation analogous to Laplace equation derived earlier for incompressible flow, normally being done in your earlier aerodynamics 1 subject. All right. However, unlike Laplace equation, which is linear, right? So the exact velocity potential equation for compressible flow is non-linear. So by making suitable approximations, we can then linearize this equation. This is where the topic on linearized velocity potential equation comes in and apply to thin airfoil at small angle of attack, right? So the results enable us to correct incompressible airfoil data that we learned earlier in the previous subject, not this subject, okay? For the effect of compressibility, so-called decompressibility correction. So we, under linearized velocity potential equation, we will look at Prudential-Glauert compressibility correction, because earlier it is incompressible airfoil data. So now we want to use linearized velocity potential equation through Prudential-Glauert compressibility correction in order for us to solve compressibility flows, right? And finally, right, and then of course, improve compressibility correction also we are going to look into. At the same time, we will also conclude this chapter by discussing several practical aspects on airfoil and general wing body aerodynamic at speed near Mach 1. So we will look at critical Mach number and the area rule for transonic flow. So we are not going to go into supercritical airfoil, right? So basically, that is the roadmap. We have already looked into the overview. What is the two-dimensional compressible flow subsonic over the airfoil topic all about? And we now look at the reason why we need to consider a subsonic flow over airfoil, especially for two-dimensional compressible flow. And of course, the next one is we want to look into the velocity potential equation. Let us go into the subtopic 5.2, the velocity potential equation. All right. The inviscid compressible subsonic flow over a body which is immersed in a uniform stream is considered irrotational, meaning that there is no mechanism in such a flow to start rotating the fluid element. So we assume it cannot be rotated. The flow in the system is there's no mechanism to start rotating. Thus, what happened? A velocity potential can be defined. Consider two-dimensional, steady, irrotational, isentropic flow. So we have a term here, velocity potential, normally being called as pi over there, where it is a function of the x and y direction. Okay, the velocity potential can be defined such that the velocity is equal to the change in the velocity potential, or in terms of the Cartesian velocity components of u and v, right? You can also express it in the Cartesian velocity components, the differential of the velocity potential excuse me, with respect to the x direction, and for v equal to velocity potential with respect to the y direction. So because since there are so many equations involved, so it's best to name equation this expression and the velocity potential expression as equation 1, and the Cartesian velocity components u and v as equation 2a and 2b, because we are going to refer it again and again throughout our session today. So let us proceed to obtain an equation for the velocity potential pi, which represents a combination of the continuity, momentum, and energy equations. Such an equation would be very useful because it would be simply one governing equations, which is in terms of one unknown, namely, in our case here, the pi, the pi velocity potential pi. And the continuity equation, if we look at the continuity equation for steady two-dimensional flow, which is obtained as equation 3, right? So we have density times the velocity component u, as well as density in the component of v, right? U and v over there. So solving it, you can get expression of equation 4, right? And we want to substitute equation 2a. We had earlier the Cartesian velocity component 2a and 2b into equation 4. So basically, what we want to take these Cartesian velocity components into equation 4. So we have this expression. So we name it as equation 5. All right. So we are attempting to obtain an equation completely in terms of the velocity potential pi. So hence we need to eliminate the density from equation 5. So to do this, you need to consider the momentum equation. In terms of Euler's equation, so we have to refer back to Euler's equation, where the change in the pressure equal to the negative sign of density times the velocity, and with respect to change in the velocity. Okay? So these equations holds for steady, compressible, inviscid flow. I always put down the important terms there so that we can always remember these are relevant approach, and relates to the P and V, pressure and velocity along a streamline. So it can be readily be known or be shown that the Euler's equation here holds in any direction throughout an irrotational flow, and not just along a streamline. Okay, so therefore from Euler's equation as well as from the velocity component in Cartesian form to A and to B, we can have this expression. So dP equal to minus density V dV, and you solve that, include 2A and 2B equation, you will get the expression for equation 6 for dP in term of the pi, velocity potential components in the X and Y direction. All right. So again, we want to eliminate density, right? The density term is still there. Let's move on. Recall that. So we are also considering the flow to be isentropic. All right. So hence, any change in the pressure, changes in pressure dP in the flow is automatically accompanied by corresponding isentropic change in the density. So change in the rho and density. Thus, by definition, right? So dP, the dP over d rho, pressure over change in pressure over change in the density. We have this expression in terms of the with respect to entropy. We name it as equation number 7. So the right hand side of equation 7, so this component of equation 7 is actually simply the square of the speed of sound, right? So we know that A is the speed of sound, is the square of speed of sound A2, right? So this component here from equation 7 is actually A squared, speed of sound square, right? So we then rearrange it, dP equal to A squared d rho, to be equation number 8. And then we want to substitute equation number 8 to the left hand side of equation 6. So earlier we have equation 6 over here, right? So we want to change this one, okay, where we can now, we have equation number 9. I hope you can follow through the steps from number 1 to what happened and so on. We are going very slow so that you can appreciate which assumption being made and then what equation that we are relating to. All right. Considering the changes in the X direction. So equation 9 that we have already found in the last slide and directly yields to this expression. So we want to consider changes in the X direction. So that leads us to this expression of small changes in the density over the small changes in the X direction, in terms of density and the speed of sound square with this component. So we name it as equation 10. So similarly, for changes in the Y direction, so this one is only X direction. What happened in the Y direction? We similarly express the terms in Y direction. Okay, so we will get equation 11, right? So now we have in X direction as well as in the Y direction. So we want to substitute equation number 10 and equation number 11 into equation number 5. Let us just visit quickly equation number 5. So this is equation number 5 that we have already derived earlier, right? So cancelling the density component. So we can easily cancelling the density components which appears in each term, and factoring out the second derivatives of pi, we can now obtain this expression, okay, which is equation number 12, right? Which is called the velocity potential equation, right? So we actually express it in the pi component in x and y without the density value. All right, so you can see that from there there's no density. We have already cancelling out the rho term over there, and this equation 12 is called the velocity potential equation. So it is almost completely in terms of pi, right? Only the speed of sound appears in addition to pi, right? No more density or pressure inside there. However, uh, this A is supposed to be the speed of sound, can be readily expressed in terms of pi as follows. So we want to try to reduce the equation. So as equation number 13, where since the A naught, right, is a constant, known constant of the flow. Given equation 13, give the speed of sound A, so we will get the speed of sound A as a function of velocity potential, pi. Hence, substituting equation 13 into the earlier equation 12, which is this one, the velocity potential equation, right? Okay, and yields a single partial differential equation in terms of the unknown pi only. So this equation will represent a combination of the continuity, momentum, and energy equations. All right. So in principle, it can now be solved to obtain the pi for the velocity potential for the flow field around any two-dimensional shape, subject, of course, to the usual boundary conditions at infinity and along the body surface. All right. So because equation 12 along with equation 13, right, is a single equation in terms of one dependent variable, which is the velocity potential pi. And the analysis of isentropic, irrotational, steady, compressible flow is greatly simplified over here. We only must solve one equation instead of three or more. All right. So once the velocity potential pi is known, right, all the other flow variables are directly obtained as follows. So you can calculate the velocity u and v from equations 2a and 2b. So you from there, let's just revisit equation 2a and 2b, right? Because we know already what is velocity potential value, so you can then get u and v values, right? And then at the same time, you can calculate A from equation 13. So you can see equation 13 over here, right? So you can now insert the values of uh, velocity potential pi, right? And also the known constant for A naught, right? So you can get the speed of sound values, right? And at the same time, you can calculate the Mach number. Mach number equal to V over A. You know U, you know also the V, which is the component of the velocity there, right? Square root them over A, you can get Mach number. Further on, you can then also calculate the temperature, the pressure, as well as the density, right? So in these equations, the total condition T naught, P naught, and rho naught are known quantities. Okay, they are constant throughout the flow field and hence are obtained from the given free stream conditions. Okay, so although equation 12, equation 12, let us just revisit equation 12 so that we are on track, which is the velocity potential equation, right? So although the velocity potential equation 12 has the advantage of being one equation with only one unknown, so it is also has the distinct disadvantage of being non-linear partial differential equation. So such non-linear equations are very difficult to solve analytically and in modern aerodynamics. So basically, solutions of equation 12 are usually sought by means of sophisticated finite difference numerical technique, right? Indeed, no general analytical solution of equation 12 has been found up till today, right? So this is being reported in many research, as well as being informed and noted in the Anderson book. So contrast to this situation with that for incompressible flow for low speed region, which is governed by the Laplace equation, a linear partial differential equation for which numerous analytical solutions are well known. So given the situation, normally aerodynamicists over the years by research and experiments and numerical simulation have made assumptions. They have made assumptions regarding the physical nature of the flow field, which are designed to simplify the equation 12, right? So these assumptions limit our considerations to the flow over slender bodies at small angle of attack. So for subsonic and supersonic flows, these assumptions lead to an approximate of equation 12, which is linear, right? So it's actually non-linear, but which is now being considered as linear and hence can be solved analytically. So these methods are subject to the our next section. Keep in mind that within the framework of steady irrotational isentropic flow, the equation 12 is exact and holds for all Mach numbers, okay, from subsonic to hypersonic. Right? I think you should be able to know hypersonic is normally more than Mach 5, right? So starting from subsonic, from 0.3, going into the transition, transonic, and then the supersonic, and before we go to hypersonic region. And for all two-dimensional body shapes, which is thin body as well the thick body airfoil or shapes, right? So with that, I believe it's best to stop there for a while, okay, so that we can try to appreciate what's going on, especially the velocity potential equation expression over there. So we have already looked into the step-by-step from equation 1 until equation 13 just now. So what are the limitations of the equation that we have already derived together? Okay, so with that, I think it's best for us to have a short break, okay, and before we continue to our section 5.3.